Let C be the closed curve going from 0, 0 to 1, 1 to 1, negative 1 back to 0, 0. And we're asked to integrate along the curve y e to the x squared dx minus x dy. We have a couple of options available to us, minus 2e, minus e, 0e, and 2e. What's the answer? All right, a few people have said C. I've heard some B's. I think I heard a D. Nobody wanted to go with A or E, huh? Well, that's good. It's not A or E. So what was it? D. Now, being closed isn't enough to be 0. Now, if it was conservative and closed, that would guarantee it's 0. So what do we do? Well, we look at our curve, and it's good to have a picture. And we say, well, we're going from 0, 0 to 1, 1 to 1, negative 1 back to 0, 0. And we say, okay, that's our picture. We mark arrows so we can see what's going on, because orientation matters. Now, looking at this curve, there's a comment. It's the wrong orientation. What does that mean? Which way do you want to orient? Now, some people say counterclockwise. We'll get into like there's a small, like, well, sometimes counterclockwise. Okay. So I just remember the song, to the left, when you walk the curve, keep the region to your left. So imagine you were a very small person and you were walking this curve, the region would be on the right-hand side. So wrong orientation. Now, if the orientation is wrong, there's an easy fix. Change the sign. So if people guessed B, well, that was a pretty good guess. They probably missed the orientation. So pay attention to orientation. Okay, so it's a line integral. We're going to invoke Green's theorem. This minus sign is for fixing the orientation. N sub x minus m sub y. So n sub x is minus 1. M sub y is minus e to the x squared. Now, that doesn't look like a great integral. But we say, look, let's work on it. The e to the x squared is the scary part. And if you were asked to integrate e to the x squared, should you integrate with respect to x or with respect to y? Now you're like, oh, is he going to do it? Is he going to ask? Well, because we need to know. But no, come on. It's before the break. We shouldn't do that. So, yes, why? Because it's hopeless to integrate with respect to x, but at least with y you have a chance. So we set up, it's a two-dimensional integral. So we still have to go through the two-dimensional integral setup. Integrating dy dx, so we're slicing up and down. So x goes from 0 to 1. Y goes from this curve y equals minus x to this curve y equals plus x. So now we're not even really focusing on the curve anymore in terms of like what it is, the orientation. It's all boundary for us. Well, okay, so that's constant. So you get constant y. Evaluate from negative x to x, which is really 2x. X subtract negative x. So 2x e to the x squared plus 2x. Those are both integrals we can do. Substitution gives us e to the x squared. Integral 2x is x squared. Evaluate. Don't forget to plug in 0. E to 0 is 1. So you end up with e. All right. Good times. Good times. Any questions? Cool. Well, don't worry. We're going to do more practice with Green's theorem. We're going to talk more about Green's theorem in general today. All right. So our thought for the day from Wayne Gretzky. We're in that time of the year when it gets cold. So we start thinking about winter sports. Wayne Gretzky was a very good hockey player. And, well, that's putting it mildly. Very good hockey player. And he said, you miss 100% of the shots you don't take. And this gets sort of to the idea of you want to try things, put your neck out. And it's scary sometimes to try things, because you're going to fail. And you notice he didn't say you're going to make 100% of the shots you take. That's not true. You're going to miss a lot, but you're not going to make anything if you don't try. So try, and including on the exam, try things. If you leave questions blank, you're definitely going to get 0. But if you try something, you got a chance. There's a real chance. All right, so recap from last time. I just grabbed the page we had. We were talking about variations of the fundamental theorem of calculus. We talked about line integrals are a variation. We said, there's another variation called Green's theorem. We're going to have 2 more before the semester is done. And what does Green's theorem say? If you have a region in the plane and you have a bounding curve, so C is the boundary of the region, and there's an orientation that goes on. So that's where I write the orientation so that the region is on the left when you move along C. Then you have that the integral along the curve of m dx plus n dy is the integral over your region partial n partial x minus partial m partial y dA. So the theme of these variations of fundamental theorem of calculus all say, if I want to integrate something on the boundary, it's equivalent to integrating a derivative of some way, shape, or form in the interior. Now, getting the right derivative with your boundary, you have to be careful. But they all say the same thing. Orientation is important. And it's easy for us to convince, there's always an orientation in your curve, but is there really an orientation here, in this right-hand side? There actually kind of is a built-in orientation, because the plane has this built-in orientation, but it's not so clear. So I want to just wave my hands. If what I say in the next 30 seconds sounds like crazy talk, then that's okay. It won't really matter. But I just want to emphasize orientation comes into play. So let's think about sort of one dimension. Can we orient things in one dimension? Well, so that's the number line going back and forth. And oftentimes you say, well, you have 2 sides. You have a plus infinity and you have a minus infinity. So you could orient in one of 2 ways. Which direction heads off to plus infinity, which heads to minus infinity. So there's a choice. A choice was made. That choice that was made, that's orientation. Now that's one dimension. Now I say, okay, but that's one dimension. What about 2 dimensions? So I have here the x, which I'll say this is heading to plus infinity in the x direction. And I have here the y, which again we'll say is plus infinity in the y direction. Well, what's the other orientation? Because I said there was a choice that was made. Well, you can always move it around so that x has the same moving, say, to the right, positive infinity to the right. What can you do with y? Well, now you could have y go down. So there's a choice in how we represent the plane. And we've just all agreed a long time ago that this is our orientation. So there's a built-in orientation into this 2-dimensional thing. Now, for 3 dimensions, is there an orientation built into 3 dimensions, the way we think about it? Yes, there is. And it has a name. So versus these are your 2 different orientations. This is the orientation that we pick. You remember what name goes with this orientation? It's very close by. What? It's a right-handed orientation. So it's ties to the right-hand rule. So there is orientation built into space. So, all right, that's just my orientation does exist, even though it may not look like it exists. Spiel. All right, back to our regularly scheduled discussion. Okay, any questions on Green's theorem? Other than the big one, which is, what's going on? What do these things represent? We'll get to that one. All right. Well, in that case, I think it's time for us to talk about some holy matters here. What happens if you have a region and there's a hole? Can we apply Green's theorem? Yes. We can apply Green's theorem on regions with holes. There's nothing that says you cannot be unholy. There's nothing that says you have to be unholy. Right? Holes are allowed. What's the orientation? So let's talk about the outside. And we'll use the counterclockwise versus clockwise conversation. Well, how do you orient the outside? Counterclockwise. How do you orient the inside? Clockwise. Exactly, to the left, to the left. So that's why I'm a little bit hesitant to say, oh, it's counterclockwise versus clockwise, because it depends on what's going on. Now, I want to think about this, and we can think about it in sort of two ways. So, why does this orientation work? Well, option one, we'll call it cutting. So here's the idea. Suppose we have this curve. I'm going to add a cut. And then I'm going to travel back and forth on this curve. So here's the idea. I'm going to go along, come to my cut, go in and around, go back, go around, in, around, back out. And then it's just not several curves, but it's all one big curve, all linked together. And the orientation is consistent throughout. Now, question. I've added material. And I'm doing this integral along this curve, m dx plus n dy. What's the net contribution of these two pieces? Or really, what's the net contribution here? Why is it 0? Because you're going to travel it twice. But what's the difference? Direction. And what happens when you move in the opposite direction? You flip the sign. So you say, oh, I get a contribution from traveling, say, from right to left, but then later on, when I move from left to right, I'm going to cancel it out. So adding these extra cuts, the net effect is no change at all. All right, so that's one way, is you can think about cutting into your region. Another way you can think about it is you can think about it as subtraction. So if I have my big region and I have my orientation on the outside, so a orientation here counterclockwise, we'll think of it as a plus. If I have an orientation inside as clockwise, what's the result of going in the wrong direction? Minus. So what happens is that the big integral will capture everything, or the big curve, but then the small integral says, but subtract that out. So what happens when you combine them both? You have a hole. So that's the effect. So that's another way to think about what's going on. Although that's a terrible picture, but that's a different way to think about it. So the punchline is you can work with holes. All right, so here's a problem. So let C be a union of two curves. C1 is the circle x squared plus y squared equals 1, oriented clockwise. All right, so let's Let's draw things here. So x squared plus y squared equals 1, oriented clockwise. So we're going that way, like a clock. And C2 is the circle x squared plus y squared equals 4, oriented counterclockwise. So it's a bigger circle, but oriented counterclockwise. All right. Now it says find the following. Find the following. Integrate along your curve, which really says you integrate along the union of these two curves. Ex to the 7th minus 3x squared y plus y cubed dx plus x minus log of sine squared of y plus 1 dy. All right, so what can we do? If only we had like a theorem. Purple? No, it wasn't the purple theorem. What can we do? Green theorem. Nice. So I say, hey, I have curves. I can fill in, and what I really have is I have like a flat donut. All right. If I wanted to sound fancy, I could say an annulus, but that's if I want to sound fancy. All right. So I can think of, okay, my region is this shape here. Okay. So we can convert this, and sort of the punchline of this part of the course is to say, don't do the integral they give you. Apply a technique that gives you a hopefully simpler integral. So integral over our region, and now we're careful here. We're pulling out Green's theorem. So this is our n. This is our m. What goes first? N with respect to what? X. So we take the derivative of this with respect to x, we get 1. Good. Subtract. Now what? Derivative with respect to y. What happens here? 3x squared plus 3y squared. All right, and that we have to integrate. Now you'll notice something. The things that looked particularly egregious, this e to the x to the 7th, this log of sine squared of y plus 1, went away. That was deliberate. We were trying to scare you away from doing the integral, and as given. Okay, so how do we integrate such a thing over such a region? Polar, right. We still have all these techniques, and we've learned about things. All right, so we'll switch to polar. So, in polar, integral, 1 will become 1. What will this 3 times x squared plus 3 times y squared become? 3r squared. What will the dA become? R dr d theta. Good. Where does theta go from? Yep, full circle all the way around. And r? 1 to 2, because circle radius 1, circle radius 2. And now we're almost 90% done. We'll multiply the r in, and then we'll do our integration. So we get r minus 3r cubed dr d theta. And from here, nothing too exciting happens. You get 1/2 r squared minus 3/4 r to the 4th. Evaluate from 1 to 2, and you start thinking like, why didn't we choose better numbers? Well, it happens. Okay, so 1/2 times 2 squared, that would be 2. 3/4 times 2 to the 4th will be 12. This is really it's going to be 3/4 times 16, or 3 times 4. Subtract 1/2 minus 3/4. And integrate that d theta. Well, this is all a constant. So 2 minus 12 is negative 10. 1/2 minus 3/4 is negative 1/4, but we're subtracting it, so that becomes plus 1/4. Negative 10, using my fancy marker here, is the same as negative 40/4 plus 1/4 makes this 39 over 4. And then theta valued 0 to 2 pi. So that gives us a grand total of 39/2 pi. Negative 39/2 pi. Thank you. Good. All right. Any questions? Be ready to do different things. Now you might say, is it okay for us to get a negative number out? The answer? Yes. You might say, but what does that number mean? Good question. Okay, so now we want to talk about what can you measure with these types of integrals along the boundary. And what do these things represent? Okay, so this says interpretations of Green's theorems. It really is more along the lines of what's the interpretation of integrating along a boundary. So we have vector fields, and one way we can visualize a vector field is we can think about there's a vector at any single point, which is capturing what's happening at that point. Now on a day like today, if you stepped outside, very windy. And so you could think of like, well, I could model the wind, which is the movement of air, where at any single point I say, well, how fast is the wind blowing and in what direction? So a short arrow, not very windy at that point, a long arrow, very windy at that point. And we can mark all these curves and we get a vector field. And so now in this vector field, we're drawing a curve and we're integrating around it and we're trying to measure things. Now there's going to be two things that we're going to look at. One is called circulation. So what is circulation? Well, what you're going to do is you're going to imagine that you have a particle that travels around this vector field. And then the question is, how much is that particle being pushed forward? How much is it being pulled back? Or is the vector field doing anything? So think of it as the wind. Is the wind pushing you forward? Is the wind pushing you backwards? Or is the wind not doing anything in terms of your direction of motion? So that's one topic. That's circulation. There's another topic which we'll call flux, which is just a very Latin way of saying flow. And the question is, all right, suppose you have a curve. Doesn't have to necessarily be closed, but we're going to do closed curves because we're going to deploy Green's theorem. We say how much, if we're thinking about wind, how much air is going through the curve, and is it going into the inside or is it going outside? So it's how much is flowing across the boundary, in essence, is what we're asking. So those are the two questions we want to answer. Now, if we're thinking about circulation, so F is how much we're pushing or pulling. So we have our stretch of our curve C. I should probably draw in a similar color here. So here's our C. And if I want to understand what's going on, I have an orientation. What do I need to look at? Well, let's say this is F. Now, looking at this, am I being pushed or pulled or neither? Am I being propelled forward or backwards by the force? Forward. How can you tell? It's going roughly in the same direction, right? If it was exactly the same direction, maybe it's here. It's like, oh yeah, that's really pushing me forward. Now, if I'm perpendicular, it has no effect, and of course I could, somewhere be pointing backwards. So now the question is, how do we measure all of this? Well, what we do is we're going to look at, this turned out into a longer discussion than I anticipated. I apologize. But we really care how much of the force is moving in that direction. And for that, we're going to look at F dot T. So F dot T ds. So F dot T, remember T is the tangent vector. So it's essentially saying what's the direction of C. I'm comparing the direction of F to the direction of T. And this tells me how much of F is pointing in the direction of the curve. Okay, so what's the punchline? If we want to do circulation, then we're going to look at the tangent vector. So it's this F dot T. And okay, well, that's the standard integral we've been talking about, m dx plus n dy, which is by Green's theorem. So this is Green's theorem. Partial n partial x minus partial n partial y dA. We've mentioned this before. This partial n partial x partial n partial y actually shows up in the curl. It's the last part of the curl. So Green's theorem is saying, if we're looking for the circulation along the curve, we can compute it by what's happening with this curl. Just grab the right component. So this dot k says grab the last entry of the curl. Now, spoiler alert, after break, we're going to come back and put a p there. And we're going to put a vector there. And then we're like, ta-da, new theorem. Okay. But that's something to look forward to. Okay, so that's half of it. So that's one way to think about this integral we've been looking at. What if we want to talk about flux? What do we need to look at there? Well, if I'm looking at flux, I need to look at what's happening through the boundary. Now, if my force is, say, going with my direction of motion, is any flow happening? No, nothing's coming in or out. But if I'm, say, here, what's happening? I'm flowing. And we can, since there's an orientation, we'll talk about here's the inside. This would correspond to an outflow. And this, what would that be? An inflow. So now, what do we need? Well, what we really need is not something that's moving with motion. We need something perpendicular to motion, and that's consistent with the direction we travel. So we're going to have what we call a normal, and we're calling it n. So it's an outward normal. So what's the outward normal? This is our n here. And I want to try to justify why this is normal. We called this part t, and we're like, yep, that's t. Totally reasonable. First off, are these perpendicular to each other?
Oh, wait. No. I'm sorry.
No, you're
Oh, yeah.
How do you know if two things are perpendicular? Think about taking their dot product. Change in x, change in y. Change in y, change in x, but with the minus sign. Put them together, what happens? Zero. So they're perpendicular. That's good. So this is perpendicular to our curve. How do I know it's this one versus the negation? Well, let's just try it out. Let's suppose we're up here on the top. So our curve is moving along. In this point, what's true about your change in x? Positive or negative? Negative. Okay, and our change in y is 0. So if we want to be going out, well, dx is negative, so you'll notice negative dx is pointing up. We can pick a different part of our curve. Maybe, let's say down here. What's true about your change in x? Positive. Change in y? positive, and we should be pointing in that direction for our normal. So what do we want? We want change in x is positive, change in y is positive, but the normal should have the change in x positive and the change in y be negative, which is consistent. So it truly is the normal. All right, well, so we take our line integral, f dot n, and this is where we start getting confusion. So be careful. Minus m dy minus n dx. Apply Green's theorem. Now Green's theorem says whatever's attached to the dx, take the derivative of that with respect to y. Whatever's attached to the y, the dy, take the derivative of that with respect to x. So that's why we get partial n partial x, subtract partial n partial y with a negative. And now the fun part, two wrongs, or in this case two minus signs make a plus, and we get partial n partial x plus partial n partial y. And spoiler alert, it's already written down here, but what is this? Divergence. So it turns out that if I want to know what's flowing through the boundary, I can answer that by saying what's happening on the interior with the divergence. So divergence, we mentioned this in passing, it's measuring local compression / expansion. If I want to know what's happening with the circulation on the boundary, the question is what's happening with the curl in the interior. And curl is roughly measuring rotation, how are things spinning. So that's the two ideas. So that's some interpretations that you might have for what's going on with these integrals. And this, by the way, is a preview of our last result, which will be pretty much our last lecture. All right. Any questions? Did I do sufficiently much arm waving there? Okay. All right. Let C be the curve below. All arcs are half circles. So we have a half circle and going on the top, and then we jump along two half circles back. The question, find the flux, or equivalently the flow, through C for the following. F is equal to xy squared over 1 plus y squared I plus y sine x cubed plus arctangent yj. All right. So we're looking for flux, not circulation. Flux. So what's the integral that matches with flux? So flux through C means integrate around C f dot n. How much is going through the boundary? And we have a nice orientation here. Now, do we want to do this line integral? No. That's the whole story. We don't want to do any integrals. How can we avoid integrals as much as possible? Well, we say, look, these curves, they bound something. So let's use that. All right, so we have our region here. And we say, well, then this is the integral over our region. What do we write here? If only we saw it like 30 seconds ago. It's the divergence. dA. Okay, so we need to compute the divergence. What do you do with this entry? Derivative with respect to x or derivative with respect to y? X. Because divergence is the nice one. It says in the x slot, take the derivative with respect to x. In the y slot, take the derivative with respect to y and add. So when you take the derivative with respect to x here, what do you get? Y squared over 1 plus y squared. And note, we probably wouldn't want to take the derivative with respect to y here. So that's a victory for us. Plus, what derivative do you take here? Yes, good. Derivative with respect to y, which gives us sine of x cubed. Wait, what? All right, well, let's just go with it. Plus 1 over 1 plus y squared. Okay. Now, these things seem to be related. Can we tie those together?
Y squared.
It's like y squared plus 1 over 1 plus y squared, aka 1. It is the 1 plus sine of x cubed. Yeah. Okay, well, we have like 20 minutes left. I imagine we can figure out the integral of sine of x cubed in 20 minutes. But do we need to? It's a rather peculiar function, a strange function, a weird function, a very unusual. Some people might even say that it's a strange function, a weird function, highly unusual. Some people might even say it's odd. Now it's like, wait, what? What does odd mean? Well, odd means if you plug in the negative x, you get the negative if you plug in the positive x. Now you might say, but how does that help us? Well, think of our region. We can split it down the middle. And if I look at what's the contribution for sine of x cubed on one side versus what's the contribution from the other side, what's going to happen? It's going to cancel out. So this is an odd function plus symmetry across y axis together tells us what? 0. So this is the integral over our region of 1. Now, how do you integrate 1 over a region? Find the area. Okay, so what's our area? Well, think of it as half a circle of what radius? So 1/2 a circle of radius 2, but that's not right because there's these pieces, so what do we need to do? Subtract 2 copies, which are half of a circle of radius 1. And if we put that all together, what do you get? Pi. So this problem, as easy as pi. All right. They like doing these kinds of things for these things. All right, I have a fun one here. I'll just save that for Friday because I want to get to surface area. So, surface area. What's our goal? Well, basically it's what you think. Our goal for surface area is we want to find the surface area. So, we have a function upstairs, z equals f of xy, which is not flat. Flat things are too easy. It's all wiggly. And the question is, well, how much area is in that surface over our region R? So we say, well, how do we do anything in integration? We break it into small parts, and look what happens. So we're thinking about, let's take this R. We're going to just look at a little teeny piece of R. So here's our little tiny piece of R. And when we look at just a small piece of R, we look at our surface upstairs, Well, it may be very wiggly in the big. When you look in a small piece, what tends to be true? It's very flat. Is it perfectly flat? No. But it's very close. The smaller the piece, the closer it is to being flat. So we say, aha, we can approximate this by a nice parallelogram. So we can approximate because it's very flat. And what's nice about parallelograms? They're easy to work with, and we have ways to find area. What's our tool for finding area for parallelograms? Cross product. So here's the idea. This flat thing is really our tangent plane. And we have formulas for our tangent plane. Now, one way to think about it, if we think about it in terms of linearization, is change in z is fx change in x plus fy change in y. So if this is my point, then my change in x is down here. My change in y is here. Then I can say, well, what happens? What are these vectors upstairs? Well, the one above where I only change x, there's no change in y, so it's change in x. My change in z follows the tangent plane. For the part above, only the change in y, there's no change in x, and then the change in z follows my tangent plane. I have the two sides of my parallelogram. I throw in the cross product formula, and it's not very exciting, so we skip the computation. But it turns out that when you take the cross product, you get negative f sub x, negative f sub y, 1. We're going to see this vector again. This is a very useful vector. Come back on Friday if you're in town, you'll see why. But we need to take the magnitude of that, so you get the square root of 1 plus f sub x squared plus f sub y squared, and then your bit of area. So what's the surface area formula? You're adding up these little tiny pieces. As your pieces get smaller, the approximation gets better. So technically this is just an approximation, but the approximation becomes exact in the limit. So it's the integral over your region of the square root of 1 plus f sub x quantity squared plus f sub y quantity squared dA. Looking at this, your initial reaction is, I don't want to do surface area problems. That is a good, reasonable reaction. Most of the time, you can't do it straight up. There are a few cases where you can, and pretty much we will do all of them. But the good news is, there's other things that we can do which involve surface areas. So that's the theory of surface area. We have time for one example. Any quick questions about theory? Our example. Like I said, we can do some. Find the surface area of the saddle, z equals x squared minus y squared, over the region R, from x squared plus y squared less than or equal to 2. The saddle is not a volume of revolution, so we can't apply Calc 2 tools. So this truly is something we couldn't do using Calc 2. So what do? We say, well, there's a formula. It's the integral over our region of the square root 1 plus f sub x squared plus f sub y squared dA. So let's take these derivatives. This x squared minus y squared, that's our f of xy. What is f sub x? 2x. So it's 2x quantity squared. What is f sub y? Minus 2y. Now, do not give in to the temptation of like, oh, Steve, you're doing it the hard way. This square root, just take the square root of each term and add. No, that's not how it works. Be smart. Don't start. Okay. So, we get integral over our region, square root, 1 plus 4x squared and 4y squared. I'll pull that out. Can we integrate this in some way, shape, or form? And if we can, what do we do to do it? Turn into r. What's the clue that we're going to use polar coordinates? Because when we say r, it's polar. Yeah. If you see x squared plus y squared as a function, and it's also showing up in our bounds. Okay, so we switch this into polar, integral, integral. What does our function become? Square root of 1 plus 4r squared. dA, r dr d theta. Where will theta go from? 0 to 2 pi, full circle. There's no restriction. What about our r? Where do we go from? 0 to root 2, because it's a circle of radius root 2. Okay, so I'm just going to make a quick observation. This is an integral we can split into two integrals, 0 to 2 pi d theta. We'll talk about that integral, 0 to root 2, square root 1 plus 4r squared r dr. Okay, the integral from 0 to 2 pi d theta, no big surprises. What do you get? 2 pi. Nice. How do you integrate the square root of 1 plus 4r squared times r dr? U sub. Yes. U 1 plus 4r squared. du will be 8r dr. Using our advanced marker technology, we'll move the 8 across. 1/8 du is r dr. So this would become the integral from, what's our lower bound going to be? 1. When r equals 0, u equals 1. Our upper bound? 9. And then this will be u to the 1/2. And then the r dr is a 1/8 du. Okay, what's the integral of u to the 1/2? U to the 3/2 and a 2 over 3. Evaluate from 1 to 9. You can cancel a little bit there, so you get 1/12. Does anybody know 9 to the 3/2? If it helps, 9 cubed is 729. 27, right. Square root of 729 is 27. It didn't help, by the way. It's easier to say square root of 9 is 3, and 3 cubed is 27. I was just being silly. Okay, 1 to the 3/2. 1. 27 minus 1. 26. So you get 26 over 12, which is the same as 13 over 6. But remember, you also have the 2 pi, so you get 2 pi times 13 over 6, which you can cancel a 2, leaving 13/3 pi. All right. We made it through an example.